You've probably heard this before. In the double slit experiment, if you observe the electron, it behaves like a particle. If you don't, it behaves like a wave. It's repeated like some deep insight, as if the universe somehow knows when it's being watched, as if reality itself responds to your gaze. But here's the uncomfortable truth. That's not what actually happens. This version of the story has been told so many times by textbooks, teachers, YouTubers, even physicists, that it became something else entirely. A simplified tale, a misunderstood metaphor, a kind of pop science magic trick that hides what's really going on. Richard Feynman, one of the most respected physicists of the 20th century, said that the double slit experiment contains the central mystery of quantum mechanics, and he was right. But the mystery doesn't mean what most people think it does. The real lesson of this experiment isn't that reality changes when someone's watching. It's that the very idea of reality might never have been what we thought. And that's why this video exists. Not to repeat the usual story, but to rebuild it based on what the physics actually says, and let you connect the dots yourself. If questions like this fascinate you, if you like carving out space for doubt in the middle of certainty, consider subscribing and turning on notifications. The algorithm rarely brings videos like this to you by accident, but sometimes a little controlled confusion is the clearest lens we have. Imagine an experiment so simple, you could recreate it with a flashlight, a piece of cardboard, and two tiny slits cut with a razor blade. And yet, so strange that even after a century of study, it still makes physicists uneasy. The double slit experiment is one of the most famous paradoxes in science, because it doesn't just tell us something about electrons or photons. It reveals something fundamental about the structure of reality itself. If you let particles pass through two slits without interfering, they behave like waves, not like bullets shot from a gun, but like ripples, spreading, overlapping, canceling, and reinforcing each other. And even if you send one electron at a time, the wave pattern still shows up, which forces us to ask a deeply uncomfortable question. How can something be in two places at once? For a long time, the explanation seemed straightforward. Because you're not observing it. As soon as you observe it, the particle collapses into a single path. But that story, while popular, is dangerously misleading because it creates the illusion of understanding. It feels like you get it, when really, you've just accepted a shortcut, a placeholder, a mystery hidden under the word observation. But what exactly changes when we measure? Why does placing a simple detector alter the entire outcome? These aren't just philosophical questions. They go right to the heart of quantum mechanics. As physicist Sean Carroll, professor at Johns Hopkins and author of Something Deeply Hidden, explains, quantum mechanics doesn't say reality depends on consciousness. It says the world at its core isn't made of solid things. It's made of possibilities. And that's exactly what the double slit experiment exposes. Not a universe waiting to be watched, but one that evolves moment by moment through interactions. Now maybe you're wondering, so what? Why should I care? What does this have to do with me? It's a fair question, and the answer is simple. Because understanding this changes how you see reality. If the most basic building blocks of nature don't truly exist until they're measured, what else is suspended in that cloud of potential? And more importantly, what exactly is a measurement? Is it a machine, an eye, a conscious mind, or is it something deeper? These are the questions physics has been wrestling with for decades. And the most surprising part is, you don't need complex equations to follow the path. You just need one thing: the willingness to look closer. So before we move on, do you believe reality exists independently of you? Or does it become real only when something or someone interacts with it? Let me know in the comments. We'll come back to that later. The history of physics is, in many ways, the story of a long war against common sense. For centuries, we believed the world was made of solid objects, standing still, obeying simple, predictable laws. A ball rolls because someone pushed it. Light travels in straight lines because that's what we were taught. But in the early 20th century, this entire worldview began to crack, not because of abstract philosophy, but because of experiments, and among them, one stood out for its simplicity and for how deeply it shook our understanding of reality: the Double Slit Experiment. This experiment doesn't just teach us something about electrons or photons. It shows us that reality itself may not be made of things, but of probabilities, not certainties, but tendencies. And that alone should give us pause. Imagine this setup: a machine that fires one electron at a time toward a wall with two slits, side by side. Behind the wall is a screen that registers each electron's impact. Now, if electrons were just tiny balls, you'd expect to see two piles of impacts lining up behind the two slits. That would make sense. But that's not what happens. When scientists ran this experiment, sending one electron at a time, they saw something else: an interference pattern. Bright and dark bands, just like waves that pass through two openings and interfere with themselves, as if each electron was going through both slits at the same time, interfering with itself, then choosing where to land on the screen. This brings us to our first premise. Electrons don't follow one single defined path. Instead, they exist in a superposition of all possible paths. This idea was made famous by physicist Richard Feynman, who described it using his sum over histories model. According to this view, every particle takes all possible paths simultaneously. What we see is the result of their interference. And this isn't just a poetic metaphor, it's math. It works. It predicts results with astonishing precision. But then comes the twist. When we try to observe which slit the electron goes through, the interference pattern disappears. We go back to seeing two simple piles of dots, one behind each slit, as if the electron was forced to make a choice. And that's true, but not for the reason most people assume. The change isn't triggered by conscious observation. It's not your eye or your mind that collapses the wave. It's the physical interaction with the measurement device. The mere act of placing a detector near the slits, whether anyone reads the data or not, is enough to destroy the interference. Here's the crucial insight. The wave function isn't just a mathematical trick. It's real. It doesn't tell you where the electron is, but where it might be, and how likely each option is. This wave function is what passes through both slits. It's what interferes. When the electron interacts with the detector, that wave collapses. The electron manifests in a specific location. But what collapses isn't the particle, it's the possibility, and that changes everything. At this point, it's tempting to treat this as a quirky technical detail. Something weird, sure, but confined to the tiny world of quantum physics. Except it's not. Because as the microscopic world, the foundation of everything, doesn't behave like an objective, definite reality, why should the macroscopic world be any different? The difference isn't in the nature of things, it's just in the scale. Uncertainty, it seems, is built into the fabric of existence, but it becomes hidden when we zoom out. And so, a disturbing thought emerges. What if the universe doesn't decide on a single reality until something forces it to? That sounds absurd, I know, but think about it. When you're not looking outside your window, the sunlight is still there, right? Or is it? What if the light only becomes light when there's something to detect it? It's counterintuitive, but here's our second premise. A measurement doesn't reveal something that already existed. It creates the outcome. Quantum mechanics doesn't claim that the world is an illusion or that nothing is real. What it suggests is something subtler and stranger. Reality is fundamentally interactive. The properties of a particle don't exist absolutely. They arise through interaction. This is called contextuality. It means that reality isn't waiting out there, fully formed for someone to see it. It's built, moment by moment, by the relationships between things. This idea was shaped by pioneers like Niels Bohr, Werner Heisenberg, and John Wheeler. Bohr introduced the principle of complementarity, the idea that particles behave as waves or particles depending on how you set up your experiment. Heisenberg revealed that it's impossible to know both a particle's position and its speed with absolute precision. And Wheeler went further. His delayed choice experiment showed that a particle seems to decide how to behave after it passes through the slits, depending on whether we choose to measure it or not. As if reality isn't fully determined until it has to be. Of course, this challenges everything we're used to. But maybe that's the point. As Sean Carroll once put it, quantum physics isn't weird. We are just not used to how nature actually works. We live in a world where objects stay where we left them, where time flows in one direction, and where things appear solid and stable. But that world is just an approximation, a fuzzy shadow of a much deeper structure. And that leads us to our third premise. There is no electron out there behaving mysteriously. The electron is the wave function until the moment it interacts. In other words, reality isn't made of things. It's made of relationships. Every particle is a cloud of potential. What it is depends not on what's inside it, but on how it connects to. It's supported not just by the double slit experiment, but by the full mathematical framework of modern quantum mechanics. Today, physicists largely agree on the experimental facts. The real debate lies in how we interpret them. Some prefer the Copenhagen interpretation. Others lean toward many worlds, or Bohmian mechanics, or objective collapse theories. Each tries to explain why the wave function collapses, or whether it really does. But none of them deny the central result. The interference pattern is real, and it would be impossible if particles were just particles. So now we've reached a curious point. So far, we haven't handed you final answers. What we've offered are premises, observations, and an invitation to think differently. Because maybe, just maybe, the modern physics that feels so confusing is really just asking us to reframe the question. Not what is real, but what makes something real. And maybe that's where the true experiment begins. If quantum physics already seemed strange, get ready, because now that strangeness becomes revelation. Let's return to the double slit experiment, but this time with a small twist. Instead of using electrons, we'll use photons, particles of light. And rather than firing many photons at once, we'll fire a single photon at a time. So what would you expect to see? Most people assume that a single photon, being a particle, would pass through one slit or the other, forming two blurred spots on the screen. But what actually happens is the opposite. Even when photons are emitted one by one, over time, they still form an interference pattern, the same wave-like structure we saw with electrons. This tells us that even an isolated photon seems to interfere with itself. Light, even when stripped to a single packet, still behaves as a wave. And that brings us to an unsettling idea. The individual particle doesn't exist as something concrete during its flight. It exists only as a probability cloud, a wave of possibilities. It only becomes a thing when it's measured. And if even light behaves this way, we're left with something even deeper. Light and matter behave the same way. What's true for the photon is true for the electron, and likely true for everything else. In other words, everything we call real might only exist as possibility until interaction forces it to manifest. This means the universe isn't built from things, but from potential relationships between systems. The particle is a useful abstraction. What truly exists is the likelihood of a future interaction. That's not just a shift in physics, it's a shift in ontology. We're not just rewriting how the world works, we're redefining what the world is. And that leads us directly to the next unavoidable question. What makes the wave function collapse? Why does the universe, calmly vibrating in probability, suddenly choose one outcome? For a long time, the mainstream answer was measurement. And since measurement is often performed by conscious observers, some interpretations claimed that consciousness itself causes reality to collapse. This idea was known as the von Neumann-Wigner interpretation, or consciousness causes collapse. But it's largely rejected today. Most modern physicists don't believe human consciousness plays that role. But the problem remains. What counts as a measurement? Is it a sensor, a photon, a molecule, a rock? This uncertainty led to alternative interpretations. One of the boldest and most widely debated is the Many Worlds interpretation proposed by Hugh Everett in the 1950s. It avoids the collapse altogether by proposing something wild. All possible outcomes happen. If you measure an electron and find it passed through the left slit, there's another version of you in a parallel branch of the universe who saw it go through the right. The universe is constantly splitting, creating an unimaginable number of realities. There is no wave function collapse, just branching realities. Every outcome is realized somewhere. Mathematically, it's clean. Philosophically, mind-bending. Where are these other versions of you? Can you reach them? Do they matter? Are they real in any meaningful sense? On the other end of the spectrum is the Bohmian interpretation, sometimes called the pilot wave theory. It proposes that particles always have defined positions, guided by a hidden wave. This restores classical causality, but requires accepting radical non-locality, instantaneous connections between everything in the universe, regardless of distance. These interpretations aren't just academic debates. They show something more profound. Physics does not yet fully understand how reality becomes real. The experiments are reliable. The data is solid. But what they actually mean remains an open question. And this is where philosophical premises begin to shape scientific conclusions. If we believe the universe must be objective and independent, we lean toward Bohm. If we believe that outcomes don't exist until interaction, we fall into Copenhagen. If we refuse to accept collapse, we must embrace branching universes. Each option carries assumptions about the nature of reality. None are neutral. Now, let's take it even further with the quantum eraser experiment. Here, you can choose whether or not to erase which path information after the photon has already been detected. And yet, miraculously, the interference pattern reappears or vanishes depending on your future decision. It seems like your choice in the present can rewrite what already happened. Physicist John Archibald Wheeler once said, "The observer plays a participatory role in reality." Not metaphorically, literally. By choosing which kind of experiment to do, the observer determines what aspect of reality is allowed to manifest. And this isn't speculative mysticism. It's backed by mathematical predictions. If this idea is true, then we're looking at a universe incomplete without observers. A cosmos that in its deepest form requires interaction to exist. But let's be clear, this doesn't mean the universe depends on humans. An atom can measure another atom. A molecule can collapse a wave function. Consciousness is not required. Interaction is. That's the key idea. Reality isn't defined by minds, but by relationships. The wave function is a description of potential. Collapse is the moment potential becomes actual. As Aristotle might have said, it's when potentia becomes essentia. And perhaps the most uncomfortable realization of all is that this applies to everything, including you, your body, your mind, your memories. They emerge from quantum processes, from particles that don't have positions until they're measured, from atoms that aren't solid little balls, but probability patterns dancing through invisible fields. If reality is constructed by interactions, then so are you. Your identity, your thoughts, your sense of self, they are stable patterns, yes, but they are not fixed. They emerge from continuous engagement with the world, with others, with time, which brings us back to the double slit experiment. It's not just about electrons, it's about you. About the possibility that the reality you live in, feel, and believe in might not be fully there until you engage with it, might not be ready, might be a field of potentials, only becoming real when you act. That doesn't mean you create reality with your thoughts. This is not wishful thinking, but it does mean that at the deepest level, reality is not independent of interaction, and maybe that explains why the world is always shifting, why certainty escapes us, why time flows, even when the equations don't demand it. Why there's always a gap between what is and what could have been. In the end, the double slit experiment forces us to confront a difficult truth. The universe is stranger than any fiction, and yet it works. The technologies we use daily, lasers, GPS, semiconductors, medical imaging, they all depend on quantum mechanics. They work because, as bizarre as it seems, the theory is the most accurate one we've ever had. And maybe that's why it bothers us so much. Because it reminds us, the universe doesn't have to make sense to be real. It just has to work. And accepting that might be the first step toward understanding who we really are. By now, what seemed like a quirky experiment with slits and particles has become something else entirely. It's become a question about everything. Because if the fundamental building blocks of the universe don't fully exist until they interact, then maybe our whole idea of reality needs to be reimagined. Maybe reality, as we think of it, is just one version, emerging only when something or someone decides to look. It's a bit unsettling, but it's also freeing. It means the universe isn't a closed book with all its pages written. It's more like a field of possibilities, shifting and unfolding through the relationships we create. And maybe that's the deeper message of the double slit experiment. Not that everything is subjective, not that nothing is real, but that reality is something built in real time through interaction, between particles, between systems, between people, between you and the world. We started this video talking about physics, but if you've made it this far, you've probably realized the topic was much bigger. It was about what happens when we choose to look more closely. Now, there's something else that might take you even further, and I'm not going to tell you what it is. But it's going to appear here on your screen in a moment. Click it. Thank you for watching, and I'll see you in the next video.